and back. Let's prove the nested intervals theorem. So let's remember the nested intervals theorem. Nested intervals theorem says if you have a nested sequence of closed bounded intervals, then the infinite intersection is non-empty. And there's a stronger version of that called Cantor's intersection theorem. But I think we'll leave it here, nested interval. All right, I think there's a sales pitch at the end of this for an extra credit. All right. So let's let I1 containing I2 containing I3 be a nested sequence of closed bounded intervals. I want to show that this infinite intersection is not empty. Let's suppose for the sake of contradiction that this infinite intersection is empty. And I'm going to use compactness to do this. To do this, I'm going to try to cook up an open couple that has to do with this fact that the infinite intersection is not empty. And you know what? Let's try to do it here. So, I know it says here what the open couple is I'm going to use. So let's see, if the infinite intersection I1 intersect I2 intersect equals empty set, then here is a way of building an open subset. So there is I1. It's closed. But that means that all of this is open. I2 is a little bit littler than it. There's I2, also closed. But that means that all of that is open. The complement of a closed set is an open set. Alternately, this is explicitly a union of two open intervals, so it's open. So I'm getting these open sets that are getting increasingly big. And what's the only thing they're going to miss? They're going to miss anything that's in the infinite intersection. But we assume the infinite intersection is empty. So things like these cover the set of real numbers. That is, if I1 intersect I2 intersect is empty. So there's a bit of motivation. That's not part of the proof. So here's what I'll do. Let's let mathcalf be the set of all things of the form real numbers set minus the kth one of these intervals, where k is a natural number. Let's prove that this f is an open couple of all the real numbers, but the real numbers are compact. I'd rather have an open couple of a compact set. They're an open couple of I1. So let's do that. Let's start by explaining why every element of f is open. Let's see. If u is in f, then u is equal to our set minus ik for some k in n, as ik is a closed bounded interval, ik is closed. Right? It's only got to be closed is one of the adjectives used to describe it. Thus, our minus ik is open. Complement of an open set. The complement of a closed set is closed. Maybe I'll put that in parentheses, since the complement of a closed set, missed the E, is open. Goody. So, there's one of the elements of being an open couple. It's a collection of open sets. Now, let's explain why it is a couple of I1. So let's let x be an element of I1. let's see. Since by assumption the intersection of all ik's from k equals 1 to infinity is the empty set, x is not in the infinite intersection from k equals 1 to infinity of ik. So what does that mean? That means x is not in every single one of those sets. The infinite intersection is things that are in every single one of those sets. So x is not an element of ik for some k. So x is in our set minus ik, which is in F. Thus, F covers I1. And there's a jump here. Since I1 is compact, let's explain why I1 is compact. I1 is a closed, underline that, bounded interval. The whole big complicated thing that you just finished listening to the proof of is the Heine-Borel theorem. C is compact if and only if it is closed and bounded. This set